Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show us thermal analysis of a spherical vessel which is insulated with different materials. After getting the results from this thermal analysis, we will validate these results with respect to manual calculations. This is the spherical vessel which is consisting of 3 different materials. To understand the geometry, let us cut this model from front plane. You can see the material. It is having 3 different materials. The inside material is polyurethane, second one is neoprene, and the third one is glass. And each one is having thickness 50 mm. Inside diameter of the first one is 200 mm and OD is 250 mm. Similarly for the second one, ID is 250 and OD is 300. And third one, ID is 300 and OD is 350 mm. Okay, we should know the thermal conductivities of these 3 different materials. First one is polyurethane. Its thermal conductivity is 0.02 watt per meter degree Kelvin. Second one is neoprene. Its thermal conductivity is 0.06 watt per meter degree Kelvin. The third one, glass, which is having thermal conductivity as 0.16 watt per meter degree Kelvin. And as a boundary condition, we are providing the inside surface of this first shell with a temperature of 140 degrees centigrade, and the outside temperature will be 30 degrees centigrade. So in this problem, we have to find out the interface temperatures. There is a temperature at this location, that is after this first shell, and at this edge. Let us consider temperature at this first location is T1, this is T2, T3 and T4. T1 equal to 140 degrees centigrade and T4 equal to 30 degrees centigrade. We have to find out the temperature T2 and T3. Okay, so first of all, we'll find out this temperature using thermal analysis, and later on we'll validate these results with respect to manual calculations. Okay, so without wasting time, let us start this simulation. Complete view of this model, and we'll start simulation from here. We're going for a new study. Let us provide the name of this one as thermal conductivity with insulator. Again, check. First of all, we have to provide materials for these different parts. It is actually assembled. You can see the parts have already been provided. The first one is actually polyurethane, second one is neoprene, and third one is acrylic glass. So we have to provide material. We're starting from the inside one. Apply edit material. We know that the first material should be having thermal conductivity 0.02 watt per meter degree Kelvin. That is polyurethane. So let us take that material from here. It will be definitely plastics. You can see a polyurethane. So we have to change the properties of this polyurethane. Let's see here, in this case polyurethane thermal conductivity is not provided, so we have to modify the property of this polyurethane with a specific thermal conductivity. Let us provide some material here. As a custom material, we will provide a new category and provide the name of insulators. Polyurethane property we have copied, and that to be pasted there. As a custom material, we'll paste this one here. Now we can modify these properties, and we can rename this one as category name is insulators and name is polyurethane cross-linked. We can modify this one as modified polyurethane, and we can provide the thermal conductivity as 0.02 watt per meter degree Kelvin. Apply, closed. So first material we have defined. Second one is neoprene, that means inside one. So again, apply edit material. You can select this one from rubber. Neoprene is there. We'll copy the properties of neoprene, because in neoprene, if you see, we don't have the thermal conductivity values. So we'll copy this property and modify these values. We have copied this one, and that property will be pasted in our custom materials. Now you can see in custom material we got neoprene, and that property should be changed with the value of thermal conductivity. Here we don't have any values of thermal conductivity, that to be updated with 0.06 watt per meter degree Kelvin. Apply, close. So we can see the second material has already been applied, neoprene, and we can provide the name as, okay, we didn't provide any name, it is neoprene only. And the outer one, acrylic glass, that to be updated. So apply edit material. Glass we can have from here, from general glass fibers. We can have the first one, and that property we can copy it, and that we modified with a specific thermal conductivity. Here we can see that thermal conductivity is not there, that we updated from the customs materials. So we can update here, paste the property of glass material, and that to be updated with specific thermal conductivity. So we can modify the name as modified glass fiber, and thermal conductivity will change to 0.16 watt per meter degree Kelvin. Apply, closed. So we have applied all the material properties. Contact resistance we are not following, and we are having bonded type of contact in between the different materials. Let us provide thermal loads. We have to provide temperature at the inner surface and outer surface. For providing thermal loads, better to cut this model from front plane. Green check. Now we can provide the thermal loads. The inside surface should be having temperature 140 degrees centigrade. So we can change the unit from Kelvin to degree centigrade, and the temperature will be 140 degrees centigrade. Let us select the inner surface. Green check, done. Now you can see the complete view of a model, and apply another thermal load, as the temperature of outside surface should be 30 degrees centigrade. Select the top surface, green check. So all the boundary conditions have been applied properly. Now we can go for meshing and running. Initially we'll mesh it with fine quality mesh, create mesh, and we want to have finer mesh. Started meshing. Meshing is done. Now we can go for running this model. Let us run this study. The solver window has started iterations. You can see it will take some time for getting all these results. Let the iterations move on. Whenever it is finished, we'll go for analyzing these results. So it is finished. Now you can see the temperatures. For understanding the temperature in a better way, we can change the unit from Kelvin to degree centigrade. So let us edit these thermal results. Edit definition. And temperature we are changing from Kelvin to degree centigrade. Green check. Now we want to find out interface temperatures, that means temperature T2 and T3 in between different materials. Okay, we know that first temperature T1 was 140 degrees centigrade and T4 was 30 degrees centigrade. In between we want to have the temperatures T2 and T3. Okay, for getting the temperature, let us take a sectional view of this model. Then you can see it's properly like, so these are the different sectional views. Okay, so let us see the results. We can see the results from the probe, and across different circumference we can see. So first one is, this is T1 and this is T2, this is T3. So in this way we can find the different temperatures. Okay, we see the temperatures from probe, and we want to see the temperature on selected entities. This is temperature at the inner surface, T1, and this one is T2 temperature. Let us see this one. It is the location it is showing that it is a neoprene, that is a second one, phase 1 of neoprene, that is inside surface of neoprene. Okay, it is showing phase 1 of neoprene, that is the second material. And let us update different nodes. We can have temperature at different nodes. You can see on the second material, on the different nodes, we can have temperature at different locations, right? Now what we do is want to get a plot of these things. We can have a temperature across the circumference of the second material. You can see the temperature is 54 degrees centigrade. Approximately you can say it is in the range of 54.4 to 55 degrees centigrade, right? So we can say the temperature of this one is approximately 54 degrees centigrade. Okay, so you can remember this thing. The temperature of the first interface T2 is 54 degrees centigrade. That to be validated with respect to our manual calculations. So we can remember this, T2 equal to 54 degrees centigrade. Okay, close it. Next one, we will see the temperature T3, that means the second interface, right? So for having these things, we have to start with probe again, probe, and we want to see on selected entities. Let us select the third one, that means this is temperature T3. You can see this is T4, this is T3, this is T2, and this one is T1, right? T2 already got, so we have to find out T3. This is the first material, this is the second, and this is the third material. So you can have this one. Okay, right. So to get the temperature T3, again start with probe, and when to have on selected entities, let us select this one. Let us update this. At different locations it is showing different temperatures. Now we can have a plot of this one, and it is showing the temperature at the interface is 35 degrees centigrade. It is showing a variation from 34.8 to 35.5. You can say the neighbor temperature is 35 degrees centigrade, right? Now this one to be validated with respect to manual calculations. You can remember this temperature T3 is approximately, you can say 35 degrees centigrade. Okay, let us close this part. Now this results what we got, that to be validated with respect to our manual calculations, right? So we can start these things to show the manual calculations. Let us open one document. You can see the results. This is the result. We can see that if we see the thermal circuit, then you can understand how it is calculated. You can see this is the first shell with a thickness of 50 mm. All are having 50 mm thickness. Now inside temperature is T1, this is T2, this is T3, and this is T4. Final temperature is T4. T1 and T4 is provided. T1 is equal to 140 degrees centigrade and T4 is 30 degrees centigrade. From basics of thermodynamics, we know that heat transfer rate through all surfaces is equal. Even from T1 to T4, T1 to T2, T3 to T4, in all cases heat transfer rate Q dot is equal, right? Now the thermal circuit diagram, you can see this is the thermal circuit diagram. So in between T1 and T2 we have thermal resistance RTH1, in between T2 and T3 thermal resistance RTH2, and in between T3 and T4 thermal resistance is RT3. So overall heat transfer rate equal to Q dot equal to del T divided by sigma R thermal. Thermal resistance given by R2 minus R1 divided by 4 pi K R1 R2, right? This is a thermal circuit diagram. we know that heat transfer rate equal to del T divided by sigma R thermal. Del T is the temperature difference in between two surfaces, and R thermal is the thermal resistance in between those surfaces. Initially we are taking all the surfaces like from T1 to T4, so del T will be T1 minus T4 equal to, you can say here it is T1 minus T4 is 140 minus 30 degrees centigrade. Del T equal to T1 minus T4, that is 140 minus 30 degrees centigrade. And thermal resistance for different circuits from T1 to T2, T2 to T3 and T3 to T4, we have R theoretical 1, R theoretical 2 and R theoretical 3. Okay, so all these cases you can find first one thermal resistance equal to R2 minus R1 divided by 4 pi k R1 R2, and we got the value as 3.98. Similarly for the second one it is 0.884, and the third one it is 0.236. So providing all these values, you got heat transfer rate equal to 21.57 watt or 21.57 joules per second. Now as the heat transfer rate is equal in all cases, and that same heat transfer rate can be applied from T1 to T2 to get the interface temperature T2, right? So here in this case we have to find out the temperature T2, as the heat transfer rate from T1 to T2 is also equal to the previous heat transfer rate. So following that equation you can find out the interface temperature T2. Okay, let us see the temperature T2. You know the heat transfer rate equal to T1 minus T2 divided by R thermal 1, that is heat is transferred from T1 to T2. So we can say that heat transfer rate Q dot equal to T1 minus T2 divided by R thermal 1. Okay, so T1 is known, T1 is equal to your 140 degrees centigrade, and R thermal 1 is also known, and Q dot is known. So from there at 1 we can find out the temperature T2 equal to 54.17 degrees centigrade, which is clearly validated to our thermal calculation results obtained from this thermal simulation. Similarly we can find out the temperature T3 also following that equation in between T2 and T3, following the similar type of equations like Q dot equal to T2 minus T3 divided by R thermal 2. In this way you can get the temperature T3 also, right? You can see T3 equal to 35.09 degrees centigrade, which is exactly same what we got in our thermal simulation using SolidWorks. Okay, so this is our today's videos regarding thermal analysis of a spherical vessel which is consisting of 3 different insulators. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.